Hi there. This week we're going to be talking about logarithmic functions, and the purpose of logarithmic functions is to help us undo their inverse, which are exponential functions. So we can use logarithmic functions to solve exponential equations, but in their own right, logarithmic functions are, as you can guess, functions. So let's take a look at what they mean. In this video here, we'll talk about how to graph logarithmic functions. So let's start with a basic idea about the Earth's population. So let's say it's estimated at about 6.8 billion right now. We could create a nice little function if we know the growth rate is 1.05% per year, and we could write down that the population would be that initial amount times 1 plus the growth rate, written as a decimal number of course, to the exponent t, where t is the time in years. Now, if I want to know when the Earth's population is going to reach 8 billion, well, I don't know. I guess we just guess several different values of t, plug them in, and see how close we can get. So I've done a few calculations on my own already, and if I plug in 15, I ended up getting just under 8 billion. And if I plug in t equals 16, I get just over 8 billion. Well, that was pretty lucky of me. Okay, so we can see that the population will reach 8 billion during the 16th year. But is guess and check the only way we could solve this problem? It's certainly not a very good method, and certainly not one we ever want to use in class. So, what other methods can we use? Well, we know that logarithmic functions are the inverse of exponential functions, so we should be able to use that to undo that exponential equation. If I were to write down, just substituting 8 billion for p, we'd get this equation. And if we can solve that equation, then we'll have answered our question. So we'll get back to that shortly. But for now, I just want to talk about the graph of logarithmic functions. Now, what are logarithmic functions? What do they do? Hopefully, if they're going to help us solve that equation, they can help us figure out what unknown exponents are. Notice the only thing in the equation we don't know is what that exponent is up there. Okay, everything else is a nice number. So that's what logs do. They're the inverse of exponential functions. And so they're the exponent. If you take the log base a of x, the output is the exponent you raise a to get x. In other words, what is the y here? Okay, so we have the x is kind of our input to the log function, the a is the base, that's always going to be given, and we want to figure out what's that mystery exponent. Of course, since exponential functions and logarithmic functions with the same base are inverses of each other, then we have the nice property of inverses, where if we were to write it with logarithms and powers, we would get exactly that at the bottom of the page there. A very important property, and essentially it's the definition of logarithms. So on the left-hand side, you can see that if you take the log base a of a to the x, it'll tell you that exponent, x. On the other hand, if you raise a to the log base a of x, you're raising a to the exponent you need to raise a to get x. So you will get x. We'll come back to this later. For now, let's just take a look at what that graph looks like. And in fact, we've seen it before because we drew an exponential function, and back when we were first talking about inverses, we were able to reflect it about the line y equals x. So we already knew what the inverse function looked like. Because the exponential function has a y-intercept at 1, our logarithmic function is going to have an x-intercept at 1. And since the exponential function has a horizontal asymptote on the x-axis, our log function will have a vertical asymptote on the y-axis. There's all that symmetry going on. Now, remember we had two different types of exponential functions, those for exponential growth. That meant the base was bigger than 1. So we're also going to get a special logarithmic function when the base is bigger than 1. And if the base is between 0 and 1, we get a slightly different graph. It'll just come down like this. So there's y equals log base a of x, but this time the a value is somewhere between 0 and 1. Okay. Now for both of these, they have the same attributes if you check them out. If we look back at the first one, the domain is going to be the range of your basic power function, so it's going to be from 0 to infinity. The range is going to be the domain of an exponential function, a basic prototype, which is all real numbers. The y-intercept, well, we see there is none. The x-intercept would be 1, 0. The horizontal asymptote, here we've got none. Our graph grows incredibly slowly, but it does always grow. There's no upper bound on it. And our vertical asymptote is going to be the vertical line, x equals 0. Now, for our other graph, we're going to have the exact same attributes there. So let's just go ahead and cut and paste that, the exact same facts there. So please take a moment and write down both of those graphs on your blue page in the back of your book. There are two basic prototypes that you have to know by heart. Okay. Now that you've done that, let's do what we always do. We're going to go ahead and use graph transformations to draw some graphs. So if we take a look at this first one, -3 log base 2 of x plus 5, well, we can start with y equals log base 2 of x. We always start with the base in there. Base is important. That tells us the prototype that we're going to use is the one on the top of the last page, since our base there is bigger than 1. Next thing we'll do is deal with that multiplier of 3 out front. We'll vertically stretch by a factor of 3. And next we will, because of the negative part of the -3, we will reflect our graph about the x-axis. And lastly, we're going to have a shift. We see inside the heart of the function there, inside the brackets of the logarithm, we've got an x plus 5. That's the heart of the function. And it's telling us we should shift left 5 units. All right, we've got our recipe. All we have to do is follow it, and we've got our graph. Okay. So we'll start off with our basic logarithmic function that has a base that's bigger than 1. There it is. Now we're going to stretch that graph vertically by a factor of 3. So all our y values are going to get multiplied by 3. Next, we're going to reflect that graph about the x-axis. And lastly, we're going to shift that graph to the left 5 units. Now, we want to be a bit careful here. For the black, the blue, and the green graph, they all have the exact same vertical asymptote. It's the y-axis. But all of a sudden, when we shift to the left 5 units, that vertical asymptote is all of a sudden going to move out to x equals -5. Also, notice the x-intercept of the blue, black, and green graphs is all at the point 1, 0. If we move that left 5 units, it's going to go over to -4. Okay? So just being very careful about these things. Just moving that green graph over, and there's our final graph. Y equals h of x, I guess I called it above. So now we just need to report on the attributes there. So we've got the domain would be all real numbers greater than -5. The range would be all real numbers. The y-intercept, we'll see it kind of, that red graph heads down below. Looks like we've got a negative y-intercept. Of course, all I have to do is plug in x equals 0 into my function, and I'd find that the y-intercept is at 0, comma, -3 log base 2 of 5. A perfectly wonderful number. For the x-intercept, we can see from the graph it's at -4, 0. For the horizontal asymptote, we have none. We never do for a logarithmic graph. For the vertical asymptote, we have x equals -5. Okay, let's try another example here. Now here you notice the heart of the function, the brackets, the argument of our log function. We've got a multiplier in front of x. So we have to factor that before we do anything else. So we're going to start off with, I guess we're calling this function m of x. It's log base 3. If I factor the -2, it doesn't go outside of the heart, it stays inside, but we're going to create new brackets to contain the leftovers. So there we have it. 4 divided by -2 is -2 there. And so we're showing the true shift. So now we're ready to write our recipe. We're going to start with y equals log base 3 of x. Okay, we're keeping the base the same. Okay, that means that it's the prototype on the top of last page. The next thing we'll do is deal with that multiplier inside the heart. Well, if we look at -2, the absolute value of that is bigger than 1, so we're going to have a horizontal compression by a factor of 2, or a half, depending on how you say it. Also, we've got a -2 as our multiplier inside the heart of the function, so that's going to be a reflection about the y-axis. And lastly, we've got some shifts. We've got a shift that's -2 inside the heart of the function, so that's right 2 units. And that -1 outside the heart of the function, that's down 1 unit. All right, let's follow that recipe there. Sorry, I'll give myself a bit more space here. So we'll start with our very first graph. There's y equals log base 3 of x. Next thing we'll do is horizontally compress. So that means all our x values are going to get divided by 2. Well, that's interesting. That'll actually affect our x-intercept. Instead of being at 1, it'll be at 1/2 all of a sudden. Okay, all our points are going to go half their distance towards the y-axis. So there's y equals log base 3 of 2x. Next, we're going to reflect that graph about the y-axis. So now our new x-intercept will be at -1/2. We're paying close attention to where it's going. See if I can draw a nice symmetric function there. Log base 3 of -2x. And last thing we have to do is shift this over to the right 2 units and down 1 unit. So here's our -1 there. Now, currently, our vertical asymptote is underneath the y-axis. It still is. So all of a sudden, it's going to move over to the right 2 units. So it's going to all of a sudden show up right out here. Okay, and that x-intercept is going to move over 2 units as well to the 3/2. And then it's going to go down 1 unit. So it's not going to be an x-intercept at all anymore. It's going to correspond to that point there. So there's our final graph. y equals, I guess we'll call it m of x since that's what it was called here. All right, let's report on the attributes there. So for the red graph, the domain is negative infinity to 2. The range is all real numbers. The y-intercept, again, we can just plug in x equals 2 there, x equals 0 there, and we'll get the point 0, comma, log base 3 of 4 minus 1. A perfectly good number. For the x-intercepts, well, that's kind of tricky. We're going to talk about that a little bit later. We need to know how to solve a logarithmic equation. We don't know now, but we will figure it out soon. So don't worry, we'll eventually talk about that. The horizontal asymptote, there is none. And the vertical asymptote, well, we can see it at x equals 2. Okay? So again, what is a logarithm? It's the exponent you raise the base to in order to get what's inside the brackets. It is the inverse function of an exponential function with the same base. And we've done some graph sketching here. We'll need to use these logarithmic functions to solve exponential equations. And actually, we'll also see we'll use exponential functions to solve logarithmic equations. Thank you very much.